cell. This is an electrolytic cell. Just have a look. An electrochemical cell. We use chemicals to make electricity. An electrolytic cell, we use electricity to break up a compound. For example, copper chloride. Are you following me? Okay, so electrochemical cells we've done. I'm not referring to them at this point, and don't confuse them with electrolytic cells. How do you know when you look at a cell which you've got? Electrolytic cells have a battery, a source of electricity. Okay, electrochemical cells produce. So here where the battery is, I would maybe have a light, if it's an electrochemical cell, or a voltmeter. All right, so we have a battery supplying electricity, and we use the electricity to break up a chemical. Now, the first thing, when we look at this cell, can you see the short line is the negative pole of the cell. So in this case, that electrode is negative because it's connected to the negative pole of the cell. All right? This pole is going to be positive because it's connected to the positive pole of the cell. You follow me? There's nothing funny about that. Okay, now, because this electrode is negative and this one is positive, we find that in the solution, here we have a solution of copper chloride, so we have copper 2 plus ions and chlorine minus 1 ions. What do positive and negative do? They attract. So the positive ion is attracted to the negative electrode, and the negative ion is attracted to the positive electrode. All right? What will happen? Well, the copper 2 plus is going to gain 2 electrons, and it's going to form copper. So we will get some copper deposited on that electrode. All right? What do we call a gaining of electrons? Reduction. All right? So at this electrode, reduction occurs. And at this electrode, the chlorine ion is going to make contact with a positive electrode, and the chlorine ion is going to form chlorine gas plus 2 electrons. So we will get bubbles of chlorine gas forming on that electrode. What do we call a losing of electrons? Oxidation. So in the electrolytic cell, we find that at the negative electrode, we will get reduction, and at the positive electrode, we will get oxidation. All right. In terms of the theory, at the cathode, the cations. What's a cation? A positive ion. Okay. At the cathode, the cations, they are positive ions, take up electrons. There we've got the reaction, forming the metal. At the anode, the anions give off their electrons. What is an anion? It is a negative ion. In this case, the chloride ions are the anions. They give off their electrons. Yes. Attracts anions. That's why it gets so confusing. All right. Are you with me? Okay. That everybody must know. Higher and ordinary level. All right. Now, this next bit, most of it is applicable to the higher levels. Some ions are discharged more readily than others. We've already said when we did the extraction of aluminium that it's very difficult to electrolyze aluminium because it is so reactive, and to break, when it's very reactive, it violently forms chemical bonds which are very difficult to break. All right, so now, some ions are discharged more readily than others. Just very simply, sometimes if the metal is too reactive, it's very difficult to discharge it from the solution or the molten mixture. Okay? So some The metal ion at the bottom, in other words, the less reactive ones, they are easy to discharge because they don't involve such a large amount of energy. So metal ions at the bottom, in other words, the less reactive ones, bottom of the reactivity series, are discharged easily. The metals at the top are more difficult to discharge. And this happens when we look at them and it's in a watery medium. Instead of the metal ion being discharged, we get the formation of hydrogen gas. Then the hydrogen ions are discharged. So they say if the salt solution is very dilute, or if we have a very reactive metal, then we get hydrogen that will be liberated at the cathode. In other words, the hydrogen ions from the water will gain an electron and it will form hydrogen gas. All right, like that. So that is very important for the higher levels. They must know this. Now, usually oxygen is formed at the anode. The oxygen comes from the watery medium. Okay, water is H2O. The moment, usually it's oxygen, except if the salt is a halide, like in the example that I have. My salt was copper chloride. Halides are chlorides, fluorides, bromides, iodides. They are discharged easily. So if I have a salt solution where I have a halide, the halide will be formed at the anode. All right? But if it is like, say, if I had copper sulfate, then it's not the sulfate ion that is going to be oxidized. It will be the oxygen ion. Do you follow me? All right. They don't go into very large detail with this. This is just very basically. So those 3 points, very important for the higher levels. Okay. The halides will be discharged, whereas by the others it is oxygen that will be formed. Now, some chemical reactions involve light. One very well-known one, photosynthesis. If I take a plant and I stick it in a cupboard and I close the door and I switch off all the lights, what's going to happen? It's going to eventually die because it needs sunlight, because the sunlight is the energy required for photosynthesis to occur. So is photosynthesis exo or endothermic? It's endothermic. It requires light. If I take away the light, it doesn't happen anymore. All right? So photosynthesis is endothermic. So they say some chemical reactions, the energy is taken up or given off. Endothermic ones require energy. Usually in the form of heat. We have to put a flame underneath the solution and warm it up. Now, we don't have to burn plants to make them photosynthesize. We need sunlight. All right? So sometimes the energy taken up or given off is in the form of light. Magnesium, when it burns, it gives off energy in the form of heat and light, very bright white light. Do you understand? So photosynthesis is endothermic. It requires light. And I've just got the equation there for photosynthesis on the board. You should know that one. It's not a new one. Here's another one that is interesting. When we have silver salts, in other words, over here, I actually have got silver ions. Okay? So if I have a silver salt in solution and I expose that solution to light, we find now the silver ions in solution form very light yellow or colorless solutions. All right? The moment the light starts shining on that solution, we find dark grayish metal being formed. What has happened? The silver ion, under the influence of light, gains an electron and it forms silver metal. All right. So that's the other reaction that requires light. So in photography, they use the silver salts. They say the light needed to break the bonds between the silver and the chlorine ions has to have a specific frequency. In the olden days when they developed photos, what color light do they have in their developing room? Red light. Why red? Are they mad? What do we know about the frequency of light? We've done waves. And the energy of the light. Red light has got the longest wavelength. The lowest frequency, it's got the least energy. So red light does not cause this thing to happen. You understand? But the others do. Orange, yellow, green, blue, indigo, violet. Do you understand? So that is why they can use red lights, so that they can see what they are doing while they are developing the pictures. All right, so the proper frequency lies within the blue range. Therefore, red light will not affect this reaction. Okay, so silver salts need light for them to undergo a chemical change. When we do organic chemistry, there's another reaction that is helped along by light. When we test to see the test for saturation, unsaturated substances discolor immediately, but saturated ones only discolor over a long period of time if exposed to light. All right, so that would be another reaction, but we will do that when we are busy with organic. So, in a microwave oven, how does it work? Low frequency radiation, remember the electromagnetic spectrum? It starts with radio waves, TV waves, microwaves. Then infrared. What are infrared waves? Heat. Normal, your body gives off infrared. So the microwaves are even lower energy than the infrared that is given off by your body. All right. Now we use microwaves in a microwave oven, and we use it for telecommunications. But now specifically in a microwave oven, when we use it to cook food with, what happens? It is this low frequency radiation. Why do we refer to it as low frequency? Well, the frequency is directly proportional to the energy. So it's fairly low energy waves. Okay? Causes the hydrogen-oxygen bond in the water molecule. Okay, there we have oxygen, there we have hydrogen. So this radiation has specifically got the ability to affect this hydrogen-oxygen bond. Okay? The bond tends to absorb some of this energy, and it starts to vibrate. They vibrate so much that the hydrogen bonds between the water molecules are broken, and the water will start boiling. Oh no, this is the hydrogen bond. I'm on the chemical. It causes the hydrogen-oxygen bond in the water molecule. That bond begins to become excited, and it affects, if I have one water molecule and another water molecule there, the hydrogen bonds. The hydrogen bonds and the hydrogen-oxygen bond are two different things. The hydrogen-oxygen bond is within the molecule. That starts vibrating. And this causes the forces here. Because remember, in the water molecule, it's a polar molecule, because oxygen, hydrogen has one electron, oxygen has there, and then it has 4 over there. So this part of the molecule is more negative than that part of the molecule. That's the one thing. And then we said that the ability of this nucleus to attract these electrons, it pulls them in closer there. Okay, because the oxygen nucleus has a stronger attractive force on these shared electrons. That is why water is polar. Now, when I expose a water molecule to the microwave oven, these electrons here start vibrating. So obviously they are able to move slightly away from the oxygen and the water molecule. This ability or the force between one water molecule and another water molecule, the intermolecular forces here, the hydrogen bond, that is it's the intermolecular force, all right? That one is broken. And if that force is broken, the water molecules can easily escape and become a gas. Are you with me? All right. So then the bond between the water molecules are broken, and the water boils. And then it is the heat from the boiling water that cooks the food. That is why foodstuffs that don't contain a lot of water don't cook well in a microwave. Okay. grade 12s. Yesterday, at the end of the period, we had a look at the Doppler effect. Just to sort of recap, we said that the Doppler effect is the change in frequency that we hear when an object that is making a noise travels towards you and then past you at a fairly high speed. All right, and we can very often hear the Doppler effect. If you watch motor racing on television, as the motor car or the motorbike approaches the person where the microphone is, and it passes that point, you can very clearly hear the change in frequency. When it approaches you, you hear a very high frequency, you go, and then when it goes past you, go, all right. That is the Doppler effect. Now, it's very easily observed with sound, and we said very simply that the object that is making the sound wave is traveling into the sound wave that is producing on the front, but the sound wave travels in 3 dimensions, so on the back end, he is traveling away from the sound wave, so the next sound wave is produced a further distance away. All right. And we then can observe this change in frequency. If you are standing on the one side and the moving vehicle is approaching you over here, you will hear a high frequency sound, all right, a high pitch. And if the person is standing over here, this one will hear a low frequency sound, although it is the same sound that was produced. All right, now, if I am standing far away from this object and it's approaching me, I hear a higher frequency. When it passes me, I hear a lower frequency. Now, that is the Doppler effect. Now, there's a formula that we can use to work out what this change in frequency sort of entails. Now we say that the formula looks like this. FO is the observed frequency. In other words, the lower or the higher pitch that you hear. All right? V is the speed of the wave. Now, a sound wave travels at approximately, let's say, 340 meters per second. So if it's a sound wave, it'll be about 340 meters per second. U is the speed of the source. In other words, over here in my picture, it would be the speed at which the ambulance is traveling. And then F is simply the frequency of the wave produced by the object that is moving. If you put this into a formula, the observed frequency that we hear is going to be the speed of the wave. In other words, for sound, it's going to be 320 meters per second, plus or minus the speed of the source. This is the ambulance, its speed, if it's traveling at 10 meters per second, for argument's sake. Why plus or minus? Depending on whether it's approaching you or traveling away from you. If the object is approaching you, you will add over there. If the object is moving away from you, you will subtract the value. And then we can work out the observed frequency. Remember, we can make this one the subject of the formula. That one. How would we do that? If you convert the formula. Yes, I would take that side and I'll divide by it, which is to multiply with the reciprocal. People? Do you know what I'm talking about? Yes? If I have 2 over 5 times 6, and let's say this is equal to, I want it on this side, let me just quickly get some clean paper. If I have, for argument's sake, I say 10 is equal to 2 over 4 times 20. All right? If I ask you to determine that one, how would you do it? I would divide 10 by 2 over 4, which would be the same as 10 over 1 times 4 over 2. Multiply with the reciprocal. All right? And that would give me 20. So my formula can also look like the following. I can have the frequency is going to equal the observed frequency divided by V plus or minus U over V. Do you follow me? All right? And that is going to equal the observed frequency times V over V plus or minus U. Do you follow me? There's a reason why I'm showing you this. Because this formula and this one, when you look at it rapidly, you have over here, observed frequency is equal to V plus or minus U over V times F. And the other one over there, we have F is equal to V over V plus or minus U times the observed frequency. It's not two different formula. It's just a different part has been made the subject of the formula. Can you follow? You can go and memorize them if you want to. It's not a problem. It depends on what they are asking you. If they are asking you for the observed frequency, then you would use it in this format. If they are asking you the frequency of the source, well, then you have to use that one. Do you follow? Ja. Sorry, ek het dit oorgeskryf daar. All right. Do you understand? It's just a manipulation on the formula that is sometimes a bit messy. Okay, can rub this out. No, it's just sometimes some questions ask for the observed frequency and some questions ask the frequency of the signal as it is generated. And then the formula looks different and it looks like there's a mistake. Do you understand? So it's from the same formula. You can just substitute and then work it out from there as well. It's just sometimes they give you the other formula and then it looks like it's wrong because you miss out on the observed and the real frequency of the object. There. That's reg, nee. Was there anything else? What did I do? There. Okay. All right. Now, that was the Doppler effect with respect to sound. It's easier to grasp that because you've all heard the Doppler effect. When there's a noise, an object giving off a noise and it goes past you. We can also see the Doppler effect in terms of light. But because light has this extremely short wavelength, we have to observe, the Doppler effect can only be observed over extremely long distances. All right? Now, they tell us the universe is expanding. How do scientists know this? On what is this based? If I have a source of light giving off white light, red, orange, yellow, green, blue, indigo, violet, red on the one, violet on the other. If this thing that is giving off light is moving away from me, I will observe a longer wavelength. I will see not white light, but red light. If the object that is giving off the light is traveling towards me, I will see a much shorter wavelength, which means a higher frequency. So I will see blue or violet light. Can you follow that? All right? So in terms of a statement being made by scientists, the universe is expanding. One of the things that they base it on is the Doppler effect. What color light do they observe if the universe is expanding? Red light. We observe a longer wavelength because the objects are moving away from us. So they say we observe a shift towards the red frequencies. And that is then the Doppler effect with respect to light. But it's only observable over thousands of kilometers because of the very short wavelength of light. Yes. They reckon the universe is expanding. It's a spiral, and the spiral is becoming bigger, bigger, bigger. That's part of the theory, but they base the argument of its expanding is the light that is observed has got a reddish color. And they explain that with the Doppler effect of the source moving away. Ja. 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 Positioneel is eintlik presies dieselfde. Huh? Ja. Yes, because everything is moving away from that specific point. Okay.
So anything can be the center. En dis hoekom hulle laat dit aan die einde van die dinge gemaak. So as enigiemand ooit vir jou sê, don't make as if you're the center of the universe.
Can you vir hom sê I am? Yes, okay. Ja, dit is baie oulik. Dit is eintlik 'n vreemde uitkyk daarop, maar ek verstaan heeltemal. So if you were living on Mars, from where you are on Mars, the universe is expanding because you are the center of the universe there. But you're on Earth, from our point of view, the universe is expanding, making us the center of the universe at that point. Nee, dis 'n baie oulike analogie. Okay. I think I'm going to stop at this point.
Catch a weekly rerun of Today on One every Saturday morning from 9 to 11:30.
Today on One, always there.
Share with us on #LearnOnOne. Tell us what you're learning and where you're learning it from. Send us your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV. It just gets better.
Akili, 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 akili. We love to wash our hands, and this is how we do it. Wash, wash with clean water. Scrub, scrub, scrub with soap. Rinse, rinse with clean water, and then the germs will go. We love to wash our hands, and this is how we do it. Wash, wash with clean water. Scrub, scrub, scrub with soap. Rinse, rinse with clean water, and then the germs will go. Yay! Well done, soap and water. You got rid of all the germs on Achilles' hands.